Hello again, my dear students, and welcome back to a new chapter or maybe a new section with our interfacing circuit. And today we are going to investigate interfacing circuits related to what we can call the piezoelectrical effect, or sensors made or fabricated based on piezo uh, phenomena or piezo effect. So let's start sharing the slides and let's see how we are going to do this. Okay, so sorry. So piezo sensing interfacing circuit. This is our title for this today. I simply call this as a section, not a chapter, because we already started the concept of interfacing circuit 2 weeks ago when we start first with CMOS-based temperature sensors, and then we go to biomedical sensors based on OFET or FET in general, field effect transistors. And now we are turning to a new type of sensors, which are based on the piezo sensing phenomena. So I believe that most of you know already what is the piezo effect and how it works. It's an energy harvesting process as an output of pressure, force, tensile or stress, or vibrations. I believe that those who already have attended the energy harvesting course, or maybe you can visit now using YouTube, you can revisit the lecture for the energy, for the piezoelectrical materials, you will definitely know in some depths what is the concept beyond these type of piezoelectric materials. Usually ceramics are doing this behavior. One of the most famous material which is doing this behavior is barium titanate. We already have some sort of contribution in our team related to barium titanate. So this is one of the famous materials related to the piezoelectrical effect, and there are other ceramic and other materials which already do such a piezoelectrical effect. So in more specific manner, we can divide this piezo effect into three main categories: what we can call a piezoelectric, a piezoresistive, and a piezocapacitive. And simply from the name, you can understand the concept. So whenever we are considering a piezoresistive material, it simply that means that this material will change its resistive behavior, or between quotation, its resistivity, once a force is applied to the material. Similarly, when we consider a piezoelectric material, this means that this material will generate some sort of a potential difference, electrical potential difference, when this when a force is applied to this material. And finally, a piezocapacitive material means that when you apply force, then this force is converted in a form of a variation in capacity. So you can understand the concept here beyond that. And again, if you return to our energy harvesting lecture dealing with piezoelectrical materials, you will find a lot of examples we have demonstrated together related to different types of sensors that can be implemented using this type of piezo effect or piezo-based sensors. But actually, our concern today is not related to the sensor itself. Our concern today is related to the circuit interfacing the sensor. As we already discussed in the previous two lectures, usually we have to use what we can call an interfacing circuit to our sensors. The purpose, or let's say the job description for this interfacing circuit is simply to convert or to process the signal detected by the sensor to a suitable signal that can be then pre-processed using other stages. For example, we usually give this example related to the ADC, or the analog digital converter. So for example, I have a piezocapacitive material, which means that whenever there is some sort of a force, this force will be converted into a capacitance. That's great. But what we need in terms of an ADC, we need a voltage variation from 0 to some sort of a VCC or whatever. So we need to convert this variation in capacitance into a variation in voltage that is compatible to the next stage with which are related to the ADC, for example. So this is the job description for the interfacing circuit in this case. So what we are going to discuss today simply is how we can build an interfacing circuit that is compatible with these types of sensors. Mainly, we will consider the piezoresistive, the piezocapacitor, and other on-off switching capacitors. So let's start. So first of all, let's consider a piezoresistive. And as we already discussed, the piezoresistive is simply the process of converting the pressure into, or the force into some sort of variation in resistance. So maybe you can say, okay, this is very easy. When I have a variation in resistance, the easy step is I need to convert this variation in resistance into a variation in voltage. I think that maybe the first thing comes to your mind in this stage is to make some sort of a potential divider. So let's go to our whiteboard and let's see. So maybe the first thing to think about it as simply is, okay, I have a resistance. So this resistance is some sort of, yeah. So this resistance is some sort of a variable resistance. That's the variation of this resistance is a function in the sensing element, which is pressure, for example, in this case, or force or whatever. So the easiest way to convert this into a variable, the easiest way is to convert this into a voltage is to make something like that. So let's put it like there, and then we have a resistance here. So I will call, let's do this VCC, for example, or any voltage. And here, let's call this R1, and let's call this RS, just to detect sensor. So the voltage here, V out, is equals to RS over R1 plus RS times VCC. And as you can see from this simple equation, that the output here is simply proportional to the variation to the resistance, RS and R1 and VCC. So R1 and VCC are constants. This is a fixed resistance, and RS appears twice in the numerator and in the denominator, and you can have a VCC here, and this is simply how you can convert resistance into a voltage. So a potential divider is a very simple way to make a resistance to voltage converter. Maybe one told us that this is somehow not a very straightforward relation because you have an numerator and a denominator function. So we can make it a bit easier by doing something like that. So we can do, so we can make it, this is RS. And let's put R1 here. And then this is V out. So in this case, V out equals to R1 over R1 plus RS times VCC. Again, the same concept is still applied, that the RS converted to the V out in terms of R1 and VCC. This is a more straightforward relation because this is typically a reverse relation, converting or connecting V out to RS. You can write it by a way or another in this format. So these are two cases where you can make a relation between your variable resistance. Again, this is not a normal variable resistance. This is a variation in a resistance due to a sensing element, a typical piezoresistive material. And here you have a very straightforward potential divider that convert the resistance into a voltage. Maybe you can add more features with that, because as we already know, my dear students, that the term correlating between the output and the input and the output, here the input is RS and the output is the output. So the term correlating these two elements is representing what we can say the resistivity of your sensor. So an incremental variation in the input will be converted to the output through this resistivity, which, as you can see, depending on R1 and VCC. This is simply can be screened by plotting this relation. So if I consider that this is RS and this is V out, which is simply the input and the output of this relation. So if I need to plot a transfer function representing the V output with RS, simply I can substitute with RS. So if RS is equal to 0, that means that herein, that means that V output will be equal to VCC. And alternatively, if RS tends to infinity, V output will tend to 0. So we will have something like that. Functions like so. The variation of this function, so simply this function is like this, or like this, or like this. You can have here a family of curves. The variation in this family of curves is simply a function in R1, which another way to construct the sensitivity of your sensor, of your interfacing circuit. So sometimes you can find that we also put this R1 to be again another variable resistance, but here this is a standard variable resistance, a controllable variable resistance, so that you can control the variation here. You can control the variation between the input and the output by controlling the value of R1. So you can adjust this R1 as value as you need to make a certain characteristics linking the V output and the RS, as you see. So this is one way to make a very simple interfacing circuit converting resistance into voltage. However, you can definitely understand that these circuits has a lot of problems. The main problem facing this circuit is what I can call, I think you already studied this more than one time before, which is the loading effect. So whenever this circuit is connected to any other stage, next stage, this resistance will will do some sort of a loading effect. Simply, if you have a next stage, a next phase in your circuit with some sort of R in here. So this R in will definitely affect everything, because now R in is parallel to R1, and then a lot of equations will change and so on. So this unisolated interfacing circuit is not the best circuit to be implemented for a sensor. That's why we start to upgrade, or let me say complicate the circuit a bit. So let's see what happened when we go further deeply with that. So as you can see, these are the two circuits I just demonstrate in my whiteboard. The first with the sensor in the upper side, and here the sensor is in the lower side, and we have this other variable resistance just to control the sensitivity or the characteristic curve between the input and the output. But let's see a more advanced circuit with that. Here, my dear students, we are using operational amplifier. I think all of you are experts with this operational amplifier, and as you can see, of course, this operational amplifier is connected with some sort of a supply, so it has some sort of a VCC in the upper side, and then a ground in the negative side, and then we have this two connecting terminals. So usually, if one of these two terminals is connected to ground, that's a basic way to have a single mode amplifier. But now, when you have two different inputs connected to the inverting and the non-inverting terminals, that means you are connecting this in what we can call the differential mode. I'm quite sure that all of you already have studied the differential mode, maybe on a gate level in electronics 1 and on a transistor level in electronics 2. So definitely you have a very good background about that. So what we can do here, that we can calculate the differential output. So let's see how we can do this on our whiteboard. This is a very simple circuit that we can do it together in order to see the effect here. So we have a VCC here. Okay. And then we have, this is RS representing the sensor, and this is R1 representing the first resistance, which is variable. And we have another branch connecting R2 and R3. So R3, I'm sorry. And the first branch here is connected. So this is our operational amplifier. Okay, just to check which in which. So This is the negative, this is the inverting, and this is the non-inverting. And then, of course, there is a supply here, and this is your output. So this is simply the circuit, how it looks like. So as you can see, we have two inputs inserted to our operational amplifier. The first is the inverting terminal is connected to this point, which is simply, we can calculate it as here, this point is R1 over R1 plus RS. As you can see here, R1 over R1 plus RS. So this is the voltage here. And typically the same, the voltage here is R3 over R2 plus R3. Okay, so and then this is the V output here. As you know from your differential amplifier classes, that the V output here is simply equals to A differential, or the differential gain, multiplied by V non-inverting minus V inverting. So we can write an equation here saying that this V out is equals to AD, or the differential gain, multiplied by the non-inverting, which is R3 over R2 plus R3, minus the inverting, which is which is R1 over R1 plus RS. So a very simple interfacing circuit appears here when you make this interfacing circuit, as you can see. So first of all, you can reach here a zero condition. So you can simply adjust. You typically know RS, or the range of RS. So you can adjust the RS minimum to be R2 over R2 plus R3, sorry, R3 over R2 plus R3 equals R1 over R1 plus RS minimum, which means that whenever you insert, or whenever your sensing element reach its minimum value, what will happen simply is that this subtraction will end to zero, which means that your output is equal to zero. The higher the RS1, the lower this term, the higher the subtraction. So your sensing value in terms of voltage will go up to reach a value which is R3 over R3 plus R2 minus R1 over R1 plus RS maximum. This will reflect the maximum output voltage. So simply, if I need to make an operation, if I need this circuit to work from 0 to 15 voltage, let's say, for example, I'm targeting that this circuit to work from 0 to 15, for example, then what I would do simply is, first, I will put R3 over R3 plus, sorry again, R3 plus R2 equals R1 over R1 plus RS minimum. So if I make this condition, this simply will end with an output voltage equal to 0 when RS is at its minimum. And then I need the maximum to be 15. So this will lead when VCC times A differential, of course, times VCC times R3 over R2 plus R3 minus R1 over R1 plus RS max. I can adjust this to be, for example, 15 voltage or whatever the voltage I need. Then, in this case, I can typically manage the variation in the output voltage, again, for example, to be compatible for an ADC or whatever the circuit is. So this is one of the cases where you can construct an appropriate interfacing circuit with a voltage range as your needs or based on your needs. And another important or another added feature in this type of circuits is the use of the operational amplifier, because as you already know, my dear student, that now this sensor is isolated because typically the operational amplifier input impedance is infinity, or realistically very high in resistance, so you ignore any loading effect in this branch. And additionally, this now is an isolated terminal because the output resistance of the operational amplifier is theoretically zero, practically very low. So again, you have isolated any loading effect for this circuit. So this is an schematic or an example for how you can construct an operational amplifier based circuit for a resistance to voltage converter. As I usually said in these lectures, maybe you hear the same words in the previous two lectures. Definitely, this is not the only circuit to do this task, and you can find a lot of circuits in literature that do or that implement the same concept. So you will have a huge trade-off between circuits. But maybe this will be part of the next lectures about power management for this interfacing circuit. But to just to examine the trade-off, the circuits in the left-hand side are very straightforward, very simple, but they have a problem with the loading effect. We complicated the circuit a bit to make it isolated, to make it differential, to control the voltage range, all this stuff, which is of course great. However, you have to consider that we pay complexity, and not only complexity, because if you remember, I showed you in the first lecture, maybe the internal schematic for this differential amplifier. So it's a very big number of transistors connected together with a lot of multi-stages amplifier. So it's not in a CMOS base. This is not just a triangle. It's more than that. A lot of transistors are inside. But it's not only that we pay complexity. We have to consider that we pay power. So if you see these circuits on the left-hand side, you will find that this is very small power consumption circuit, which just a supply is connected to resistance. So simply the overall current flowing here is VCC over R plus R. So the power is simply VCC square over R plus R. However, here you have three branches connected to supply. Typically here the power is doubled when I'm using these two branches instead of one, and then I have a third branch connected to operational amplifier, which is still consume power. So you have at least triple times maybe the power consumed in the circuit in the left hand side. So this is what you are paying. You enhance the interfacing circuit quality. That's true, because you add more feature, you add an operational amplifier as an active element. But on the other hand, on the other side, you lose or you pay more power to be consumed for your interfacing circuit. And usually when we consider these IoT and IoT square sensors, we have to keep attention or pay attention to the power, because power is a very fundamental element here. So this is an example for such type of an interfacing circuit used for resistive or piezoresistive circuits. But we may have another type of sensors which we can call that this is an on-off switching sensor, and this is, by the way, is very famous nowadays. That we don't need to have an analog sensor. This is a concept. This is an example for an analog sensor when we have a sensor that is have a variation between RS minimum and RS maximum, or between a minimum pressure and maximum pressure, or whatever. But we can have another type of what we can call an on-off sensor, or what we can call a digital sensor. So in this digital sensor, your sensor is simply acting as a switch. It's either on or off. So for example, let's say that we are using a piezoelectrical material, or a piezoelectrical or a piezoresistive material that's used for detecting if there is someone in this place or not. So it's something as a pad distributed, or it's put it on the ground floor, on the floor of the room. So if you push or if you press by your weight this piezoelectrical material, the material will work and will make some sort of a resistance. Otherwise, if no one is here, then there is no pressure, then it will be an open circuit, for example. So this is or a very high resistance. So this is a very typical example for an on-off switch for using a piezoelectric material here. So in this case, it's very straightforward. So either there is a resistance or not. So this is a very schematic, very simple schematic for that. So we have a resistance here and we have a switch here. So if there is the sensor is on, this switch will be connected in a form of short circuit, maybe, so it will be grounded. Otherwise, if the switch is off, then it will supply to the VCC or the high voltage, then you will have this high signal. So it's a very basic high-low sensing circuit. But again, we have to consider other effects. For example, we have to consider that here we have a very two important effects associated to this sensor. The first is still the loading effect. We have to consider the loading effect. So whenever you are connecting this circuit to a next stage with some sort of a resistance here, then this will distribute your concept and you will not reach this ground state. And another important parameter here is the high frequency component. If you flash back to your signal classes, you will remember that high frequency component are usually embedded in the sharp edges. So whenever you have these ideal sharp edges, you should expect a high frequency component, which is usually a problem, knowing that any system, any electronic system, as you definitely know, has a finite bandwidth. So typically, when you have these very high frequency components, this frequency component will be maybe clipped somehow when you go to next stages in your circuit. So in order to get rid of that, which we kind of call it the bunching effect, so we can use something like that. So this is a modified circuit. So still we are using the same resistance branch with our on-off switch, as you can see, but here we add some sort of a filter. So whenever it's whenever the switch is off, as you can see here, then you will have a flowing here in this direction, keeping this voltage still high because it's connected over these 2 points. This is an open circuit, as you can see, and the current will flow in this direction, making this voltage high. However, when you short circuit this point, then your charged capacitor will start to discharge gradually from this point through the resistance and then the short circuit. So you will not have these sharp edges here. You will have some sort of a smooth edges because simply this RC is acting as a low pass filter. So simply it gets rid of this high frequency component and then permitting only low frequency component to pass. That's one of the very famous interfacing circuit when you are considering what we can call an on-off switch or a digital switch. As I just mentioned in the beginning of this lecture, that we not only have this piezo electric material or piezoresistive material, but we also have another form of a material which we call the piezocapacitive material. And for me, and not only for me, maybe for a lot of electronic designers and sensor fabricators, piezocapacitive materials are one of the very famous and very booming and very interesting types of piezo materials, where you convert your pressure, your force into a capacitance. And herein, we definitely need an interfacing circuit for such type of sensors in order to convert this capacitance variation into a voltage variation. So what we are going to do in the next slides is we are going to demonstrate different types of piezocapacitive based interfacing circuits. So let's see what are the main famous types of the piezocapacitive interfacing circuits.